Fun fact, if you take any 4 points, connect them in sequence to form a quadrilateral, build squares off of each side, find the centers of those squares, and draw 2 lines connecting opposite centers, then those 2 lines will be the same length and they will be perpendicular to each other, no matter what sort of quadrilateral you start with. Even if the lines don't intersect, they'll still be perpendicular to each other and the same length, as long as the original 4 points are connected in a loop and the squares are consistently to the left or to the right as you walk around the loop. This is called Van Obel's theorem, published by Dutch mathematician Henri van Obel in 1878. There are a few different ways to prove it. The one I find most elegant involves expressing each of the 2 perpendicular lines as the sum of certain vectors. First, we'll need to connect the center points of the squares to the quadrilateral with lines that are perpendicular to the nearest side. Note that because they start off at the centers of the squares, they intersect at the midpoint of that side and are half its length. Now let's define the vectors we'll need. This one I'll call A. It takes you from one end of the leftmost side to its midpoint, or from its midpoint to the other end. Rotating it 90 degrees to the left results in a vector that I'll call A prime. Rotate it another 90 degrees and you get A double prime, which is the additive inverse of A, so we could call it negative A. With similar vectors B, C, and D for the 3 other sides, the whole quadrilateral can be traced out by adding 2 A's, 2 B's, 2 C's, and 2 D's, like this. Notice that the sum of all these vectors is 0 because they loop back to the starting point. This is, of course, also true when you add only 1 each of A, B, C, and D. We'll need this fact to finish off the proof. Okay, now let's look at the vectors that take us from one end of each red line to the other. The first line can be expressed as negative A prime plus A plus B plus B plus C plus C prime. And the second one is negative B prime plus B plus C plus C plus D plus D prime. Since we want to prove that the lines are perpendicular and of equal length, we could rotate one of them by 90 degrees and see if they are parallel and of the same length. In other words, are the vector sums now equivalent? Notice that each vector in the rotated sum has acquired a prime, since each one has rotated 90 degrees to its left. So the first vector is now negative B double prime, which is the same thing as B. And the last vector is now D double prime, which is the same as negative D. So, to prove that these vector sums are equivalent, we can subtract one from the other and see if the result is 0. This means flipping one over, attaching its start to the other one's end, and seeing if we get back to where we started. Notice that each vector of the flipped line is now the inverse of what it was before, so the negative D is now positive, and the others are now negative. Well, it certainly looks as though these vectors add up to 0, so let's prove it. First, notice that there is a B and a negative B. They cancel each other out, so we can remove those 2. There's also a C and a negative C. And now, if we rearrange the vector slightly, look at that! We have an ABCD loop, which by definition equals 0, and we have the same loop rotated 90 degrees to the right, which of course also adds up to 0. And there you have it. That finishes the proof. There are ways to generalize this theorem with rhombuses instead of squares, for example, but they're all basically the same idea. The animations for this video were generated using the Desmos graphing calculator. There's a link to this graph in the description so you can play around with it yourself if you like. Thanks for watching. Please subscribe if you want to see more videos like this, and let me know in the comments, how cool was that?